So having filmed the video talking about Newton's third definition, where he defines basically what we mean by inertia, I then did a little experiment. I put a picture on Twitter and then wrote down what Newton's definition of inertia was. That it was, in his words, it was the force that arose to oppose the change in motion of an object that has inertial mass. And so I wrote that down and asked the question broadly, is this correct? And one or two physics teachers said that yes, it was. Other teachers saw that the example used was confusing and brought about other issues. But some teachers were just completely adamant that it was incorrect and argued vociferously that my basic understanding of physics was wrong, and in one case arguing that this is not the sort of question that physics can answer, not knowing that I was quoting Isaac Newton's definition for inertia. So I think the lesson to learn from this is that generally inertia is not well understood, and it's basically because we no longer use it as a quantity, we no longer discuss it as something that is present. However, it is something that we need to have like a proper understanding of before we can hope to be able to explain why and how things move. Now, I've got a couple of extra demonstrations that I want to show you that are just interesting, that will hopefully help everyone watching this come to an idea for themselves what inertia is and how we can observe it. Right, okay, so first things first. We've got a situation here where we've got a cart that is being pulled by a weight that is over this pulley over here. And there's a spring in the middle. Now, all the spring is going to do is enable us to see when it extends, when a force is being applied relative to the two objects. When this is pulling that, the force will extend. If there's no force between them, then the spring will not extend. It's on an air track because we want to see the difference between this being a frictionless situation and a friction situation. People, of course, saying there's no such thing as a frictionless situation, but actually removing most of the friction, I think, is going to change the outcome of this experiment. So we're going to dive in and we're going to have a look at all of the various different options that this experiment is going to show us. The very first thing we're going to do is it'll be quite noisy because it's an air track and we'll have to turn that on. We'll turn that on, it'll reduce the friction, and the very first one we're going to do is see what happens when the weight is suddenly put onto the spring. So I think this is probably going to be the most revealing of all of these. The spring will be unextended, the weight on this side will be supported, and we'll watch what happens to the spring as I let go of this thing. So let's have a go. One. Oh yes. Wow, that was quite conclusive. When the weight suddenly loaded the string and tension was produced, obviously it transferred a force to the end of the spring. What did the spring do? Well, the spring extended because it didn't just instantaneously pull the spring unextended, it stretched the spring. Why did it stretch the spring? Was because the car was refusing to move. And when I say refusing to move, the car had its own inertia, and that was opposing the original acceleration of the car. So when the force acted that way to accelerate the car, what acted in response to that force, the reaction to it, was the force that arose from the car's inertia. As Newton said, the vis incita force, the force that arises to oppose the change in motion that is proportional to the mass of the object, or proportional to the inertia of the object. Now we're going to do this again, but this time I want to see what happens, and I don't know what the answer is, when we load it without dropping the load. So the spring is already extended when we let go of the apparatus. And I think it's going to produce a different result. And we don't want to confuse what it tells us, so we'll have a very careful look. 3, 2, 1. Woo! Ha! It did the opposite. That when you release the whole system, what happened was the spring actually compressed and then moved at the same level of compression along. Who guessed that that was going to happen? Well, I think the explanation for this is linked to what happens when you drop a slinky. So let's go and have a look at that. So what happened here? Well, an interesting thing. What we observed was that when the spring was extended and we let it go, the bottom of the spring seemed to stay where it was until the top of the spring had caught it up and then they moved down together. And the reason for this is that when you think about the forces acting on the bottom of the spring, there is the weight of the spring acting downwards, and this will extend the spring until it is equal to the basically the spring force acting upwards. Now the top of the spring has the weight acting downwards and the spring force acting downwards. When you let go of the spring, both parts of the spring will try to move towards each other, except that the upward moving, the upward movement of the bottom of the spring is exactly equal to its downward acceleration. So they cancel out, and so the bottom of the spring stays constant. Whereas, of course, the top of the spring has the acceleration due to gravity and also the acceleration due to the spring force acting in the same direction, which means the top of the spring actually falls faster than free fall, an object is being pulled in. Now, what happens with this experiment is it is loaded, and that is analogous to the weight acting on the bottom of this spring. The second I release the system, then the top part has both the weight and the spring force acting in the same direction, which causes the spring to compress. And then when it has compressed, what you then get is that the spring stays at a constant size as the whole system then accelerates. Some textbooks, you'll see, state that this particular situation has the spring staying fixed as the whole object moves. And this is clearly, demonstrably wrong. So, to fully explore all of the possibilities of this apparatus, let's consider what happens when this is not a movable object. So, we're going to make it fixed, and we're going to see what the effect is, first of all, with a load that suddenly applies to it, and then secondly, when the load is just released, to see if there's any obvious differences. Now, because this air track has no longer got any friction, this is a very good, it is essentially fixed, it's not going to move, or not appreciably anyway. So I'm going to release it to a point just here, and then I'm going to zoom in, and the first one I'm going to do is I'm going to support the weight and then remove the support. Sudden onset of the weight, and we're going to have a look at what happens to the spring just here. So in the first case, what happened was the weight was supported and the support was removed. That caused a sudden extension of the spring, but then it acted like a bungee cord, and it engaged in simple harmonic motion. So basically, it was like a gravity-assisted spring mass system. It just bounced backwards and forwards and forwards and forwards. To be expected. Secondly, when we just released the mass, when it was extended, it just remained extended. just like this right now. So what's curious about those situations is if it's extended now, then this is applying a force that way, and what is applying a force backwards in this case is indeed the friction. So there is the tension in the string acting that way, and providing why is the string anchored at this end, it's because there's so much friction between this and this that it cannot move, it is fixed. Now, okay, that is one way of looking at it. Another thing that you could consider is that being fixed, it's also pulling this metal part. If this whole thing was clamped and there was it wasn't friction that was holding it, it was just simply a solid structure, then what's going to happen is the pull on that clamp is going to potentially stretch or pull the atoms slightly further apart. Quite often with Newton's third law, explanations go straight away to the atomic. They look at situations where atoms or the distance between the atoms gets smaller, the spacing gets compressed, pushing the charges closer together or further apart, causing electrostatic forces which oppose the stretching tension of the string. And that is correct in this situation, because what's actually happening is the fact that this is solid and is not capable of moving means that what is essentially pulling back is the structure's ability to hold on to its own atoms, the extension, the pulling apart of the structure and the moving of attractive charges away from each other, and that attraction pulling it back. So very much in this static case, invoking electrostatic repulsion between charges is the correct way, but only in this static case. When there is the situation where one of the objects is free to move, then it becomes dynamic, and on top of any forces that are happening on an atomic scale, you also have to look at the force required to overcome an object's inertia. If you pull forwards and accelerate that object, then the tension in the string arises from the innate resistance to that acceleration, what Newton defined as the vis incita. When we talk about Newton's third law, we very rarely reference it compared to the first law. We very rarely talk about the force required to overcome an object's inertia to make it accelerate. We tend to talk about static situations, like an object where there is a force attached to it. And of course, avoiding the example of an object sitting on a desk, which of course is not an example of Newton's third law, not purely, because the weight acting down is gravitational and the reaction force is electrostatic, two different types of forces, and so it's not an example of Newton's third law. But of course, you can very easily just, you could pull it, and the resistance to you pulling it is an example of Newton's third law. So that's the example I want to talk about. This here represents a solid. It's a model of a solid. The atoms represented by these ping pong balls, and the bonds between them, the springs. Of course, this model I can kind of compress and I can distort. I might break it, but this model is flexible, just like most solid substances. And what I know is that if I try to pull it, then what's going to happen is the attractive forces of the bonds between these atoms is going to pull back. And so for a lot of situations that involve Newton's third law, it is actually entirely electrostatic, the reason why there is a reaction to whatever you're doing. Whether or not you're compressing something, there is a resistance for it to being compressed. And whether or not you're extending it, you're trying to stretch it, then there is a resistance to that as well. So that's a solid object. In a lot of the examples that we were thinking about, when we were thinking about whether or not towing an object would require you to provide a force to overcome the inertia, then one of the things that was complicating it was the action of the rope itself. And the rope itself is made out of atoms, and the atoms are just like these ones here. They have bonds between the atoms. So what I have here is I have a load of springs, and there's no ping pong balls representing the atoms, but what you just got to do is just believe me that the gaps in between these springs just represent where the atoms would be. Now I want you just to observe what happens. If I pull this and this is static, then what I find is it has the effect of pulling apart the atoms. It increases the force, and I can feel this pulling back. As I apply a force this way, it is pulling me back, and this is where the reaction pair, the action-reaction, object A exerts a force on object B, then object B exerts a force on object A of the same type. That's where it's coming from. It's coming from the fact that stretching these is pulling the atoms further apart. And whether or not I loop it around the back and cause a compression of the solid, or whether or not it's an extension of the rope, it doesn't really matter. It is always the same thing. How the example that we've been talking about is different is what occurs when this is free to move. So we have a pair of skateboards here, and we're going to put our solid on the skateboards like this. So now what happens is, as we pull it, what we might find is there is some friction in this system which prevents these skateboards from rolling. But after that, then there's no expansion of this required. There's no force required to make it move at constant speed. But if I want to accelerate this, I have to actually still apply a force, as you'll see from the extension of this. So here we go. Well, it kind of flew off. But you get the point. That when an object is static, it's a stretching of the bonds that causes the resistance to your pull. But when an object is free to move and free to accelerate, it is its inertial mass that makes pulling it so difficult. In fact, accelerating it, increasing its kinetic energy, can be said to be doing work against the force that's trying to stop you. In this case, it could even be said that rather than doing work against gravity or work against friction, that accelerating an object is doing work against inertia.